Thank you so much. Thanks to everybody. And my name is Tyler Lay. I'm a professor at Oklahoma State University. I'm representing a whole bunch of different folks you can see on the slide today, and we're super excited to be able to share some of our most recent work that we've been doing with you. Big thanks to the folks that fund us and make this work possible. Several DOTs, several FHWA, several other agencies, and a big group out there collaborating and helping us move the ball down the field. Thank you, thank you, thank you to all those people that are pushing on this. So fly ash, as you know, is an essential ingredient in concrete. You could say it's like Batman and Robin, right? You could say it's like Han Solo and Luke Skywalker. And I have to warn you just a second that I'm a massive Star Wars fan. I have Jedi robes, I have lightsabers, I hang out with Wookiees, so you might see some more Star Wars coming up from me. But as you know, coal-fired power plants are going away. Fly ash supply is going down. Cost of fly ash is going up. This is scaring people, right? Fly ash usage has the potential to go down. This could make our costs go up, our sustainability go down, our durability go down. Oh, no, no. What are we going to do? This sounds scary and crazy. Oh, no. You know, people out there are saying, you know, use other pozzolans, and I don't disagree with that. I think those are all good things. Slag, silica fume, natural pozzolan, calcine clays are great alternatives. But ladies and gentlemen, did you know we got something else? Did you know we got the backup fly ash out there? You know, the backup fly ash. What's the backup fly ash? Did you know the United States only uses about 40% of the fly ash that's being produced today, and it's been doing that for decades? Tom Adams is going to talk more about this in the second session. Make sure you check him out. So what happens to all this other fly ash that we don't use? It ends up in landfills, storage facilities, things like that. And this is the backup fly ash, ladies and gentlemen. This is good stuff, and I'm going to talk about a bit about it today. There's 2.5 billion tons of usable fly ash that's buried in holding ponds in the United States. If at our current usage level, that's 170 years worth of supply. To say that there's no fly ash out there, that's not quite right. But the future of fly ash, I think, is going to be very, very different. So our current standards, though, were written when fly ash was abundant, and we need new tools to look at the true performance of our fly ash inside concrete. We need something like this. When you walk down the aisle of your favorite grocery store and you pick up something and you go to look at it, you can see how much fat, how much cholesterol, how much whatever it has. We need that for our SCMs, and especially for this reclaimed ash. We need to know how much strength, how much workability, permeability, ASR, etc., that it's going to give us. And we're going to be using artificial intelligence to predict fly ash. I do a lot of other stuff, right? But we're going to be using artificial intelligence to try to predict this. That's tied to real performance value. So we're going to take a different approach. You know, see some out there, and we do this as well, that make very, very precise predictions using artificial intelligence models. These are great, and for their data sets, they usually work well. But when you go out into practice, there seems to be variability just in concrete that starts to really plague some of these models. So instead, we focused on grouping performance into high, medium, and low, and we said, hey, what if we could do this by only using the bulk oxides, the only bulk oxide? We have more complicated models. I'll show you a little bit of data later on about that, but what if we could use only the bulk oxides? What I mean is this. You know, you get your sheet of fly ash, you have this type of information, and you're going to use that to predict performance. And it's not going to give you the exact strength. It's going to give you is it high? Is it in the middle? Is it low? That's what it's going to tell you about a lot of different parameters. And I think we can get to all of these parameters, and I'm going to talk about some of them today. Wouldn't that be cool? I think that'd be cool, right? That'd be totally cool. So what I'm going to do here is talk about a subset of the data where we compare fly ash performance to mixtures that only contain Portland cement. That means a mixture with straight Portland cement versus a mixture with fly ash. 20% fly ash replacement and 40% fly ash replacement. I'll get to that in a second. And we're going to break up into 3 separate classes: Class 1, Class 2, and Class 3. Class 2 would be the same as Portland cement plus or minus 1 standard deviation, because every single test method has a variation. So we are the same as Portland cement plus or minus 1 standard deviation. That's Class 2. Class 1 would be Portland cement minus 1 standard deviation, so lower than that. Class 3 would be Portland cement greater than 1 standard deviation. If that doesn't make any sense to you, think of it as less than OPC, the same as OPC, or greater than OPC. We're going to use 19 different traditional fly ashes for the data I'm showing you today, but I'll give you some secrets here. We're up to 30 different traditional fly ashes, and we're up to 14 different reclaimed ashes. Things are looking really, really good with what I'm about to show you today. But we're going to test this in concrete. We're going to make a 0.45 water cement ratio, type 1 cement, 1 coarse aggregate, 1 fine aggregate. We're going to measure compression strength and diffusion coefficient for the data I'm going to show you today. But don't worry, we got a lot more data coming down the chute, right? So the data looks something like this. We've got compressive strength on the y-axis. We have days of hydration here on the x-axis. And we've got data points here. Class C ashes are shown in red. Class F ashes are shown in blue. Portland cement is shown in black. And as you can see, just because the red line here is the average Class C, the blue line is the average Class F. Just because you got the average doesn't mean anything. There's variation in every one of these fly ashes. That just means Class C and Class F is not a panacea. It doesn't tell you everything. And you're like, I knew that already. Great, cool, we're on the same page, amazing. But what we're gonna do here is let's focus on different days. We're gonna predict performance at different points in time. And we're gonna look, say, just for examples, at 180 days here. We're gonna break it into group 3, group 2, and group 1. Remember, group 3, that's better than Portland cement. Here's our Portland cement right here. Group 3 would be better than Portland cement, plus 1 standard deviation. Group 1 would be worse than Portland cement, minus 1 standard deviation. So we're going to use something called Kernel Principle component analysis. Now, I have used 8 or 9 different machine learning algorithms. I'm so blessed to work with someone that's been doing machine learning for about 2 decades. He is extremely good at this stuff. And we're going to examine all 11 bulk oxides, all right? And we're going to leave something called a leave one out cross validation. That means we're going to use 18 of the measurements to train a model, and then you check it and see how accurately did it get that one that I left out. And then you do it again, then you do it again, then you do it again. So you go over and over and over again, and every single time you say, how accurately did it get that one that I left out? And we're going to report the best from that. So here we go. So here's the question. Is the mixture less than OPC, the same as OPC, greater than OPC? And we're going to look at compressive strength. This is a 20% replacement. This is a 40% replacement. These are different days. And you can see here at 7 days, it was 89% accurate for 20% replacement, and it was 95% accurate for a 40% replacement level. Now, this is for 19 fly ashes. Now, I can tell you when you get up to 30, these numbers jump up to the low 90s. We're looking at 93 to 95% accuracy level. That's pretty awesome by only using the bulk oxides. Pretty neat, huh? We can actually predict diffusion coefficient as well. Diffusion coefficient, you know, the one that actually predicts the rate at which ions are going to penetrate inside of our concrete, right? And with 20% replacement, we're at 84% accuracy, and 40% replacement, we're at 100% accuracy. That's pretty awesome, right? So the Kernel PCA analysis is able to use the bulk oxides to group the performance for fly ash at 20% and 40% replacement level for these 19 raw ashes that I showed you today. But don't worry, we're expanding to reclaimed ashes, to non-standard ashes, to lots of other materials, and everything's looking promising. It's just not quite ready for prime time, but it's super close. Everything's looking really good. So how would you ever implement this? Well, I'm going to give you a free tool today that already works as well and is going to get better and better and better over time, where you input the bulk oxides into a simple web interface. The website will do all the calculations, and it will tell you how it's going to perform compared to OPC. It's right here. So get your pens out, take your screen captures. I know your screen capture out there. Capture this right now at tylerley.com/fly ash. This is live. This is ready to go. This is free. You type in your bulk oxides over here. You hit a button. It makes sure that you're actually using fly ash, and it calculates. Are you the same as OPC? Are you lower than OPC? Or are you better than OPC for compressive strength and for diffusion coefficient? Now, how would this ever be used? Well, you could better predict high volume performance, fly ash performance inside of concrete. You can substitute new fly ash sources without doing a mix design. And I'll talk more about that coming up. You can look at blends of fly ash. Producers are already using this to look at blends of fly ash, and it's working well, or allowing fly ash that doesn't meet current specifications. What? Well, ASTM C618 requires a lot of little bits and pieces that isn't true for all sources of fly ash, and we're finding many of these that do not meet that still work well within a certain framework, and I'll talk more about that in future talks. And then the use of reclaimed ashes is, again, looking extremely promising, and I'll show you just a tidbit of data about that at the end, because Farshad asked me to. So here is an example. Supplier has submitted a mix design with fly ash number A, and they need to swap because A isn't available anymore. Sounds familiar, right? And what they do is they run the oxide analysis for A and B, probably already have them, and then they put them in the website and compare performance. So if the performance is the same or better, allow the change, allow it to go. If the early age strength is lower, then maybe require them to decrease the water cement ratio. If the permeability isn't quite what you want it to be, then increase the fly ash content or possibly decrease the water cement ratio. We're using this knowledge and what we already know about concrete to make wise decisions on how to deal with these challenges. That's what engineering is all about, right? And this is just a tool to help you get over some of the hump. So how will this be helpful? This gives us deep insights very, very, very rapidly. And this is way better than just Class C or Class F. And we're about to enter a new era of fly ash, baby. And we need all the help that we can get. So why does this work? Well, for one reason is the particle size distribution is pretty consistent between these ashes that I've looked at. Particle size distribution is going to be important when it comes to reclaimed ashes in the future. And we're going to need to watch into that, because when some of that material becomes reacted, it conglomerates, and we need to understand that. But we've also done deep studies into fly ash before. We've been studying fly ash for more than a decade, and we've learned all kinds of generalities, like magnesium content, believe it or not, does impact strength. And we've used the machine learning to take all of these learnings and put it into one simple tool. Maybe you've seen this. You've seen a ternary diagram with silica, calcium, and aluminum, where people like to plot different SCMs. And different SCMs fall into different categories. Ladies and gentlemen, we have like an 11-dimensional ternary, whatever diagram, octadecalduca diagram, or whatever it is. And what we're doing is the machine learning is finding planes within that diagram that predict performance based on chemistries. Published lots and lots and lots on this, lots of papers out there where we've talked about some of this stuff. So what's next? We're adding more data to the algorithm. Like as we speak, set time is going to be coming out before you know it. Total heat. So if you want to do mass concrete predictions, we've got it in the bag. We're working on it. It's coming out. Resistivity model is ready to go, but I'm scared to put it out because I'm not sure if people would use it correctly. We're working hard on ASR. And what else do you want? Light the chat up. Let me know. Tell me what you want to see in the future, what you're not seeing in what I'm showing you here today. So again, I showed you this. This is the big takeaway. TylerLay.com/fly ash. Get out there and check it out. And you can see more information from me. I've got a YouTube channel at youtube.com/TylerLay. And this video, Unlocking the DNA of Fly Ash, talks a lot about complicated methods to very carefully understand and predict fly ash performance. And some example, because Farshad asked me to include one slide about it down here at the end, is where we use some of these complicated models on 4 different reclaimed fly ashes. These are complicated models. And so what is shown here in green is the predicted model, and what's shown here in yellow is the measured. You can see we're really, 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 really close. Really close, extremely close. These 2 lines are very close. These 2 lines are very close, all the way up to 180 days. This is with the reclaimed material. Now, There is one that's a little bit different. We have some ideas about why that is, but what this means is that even with this reclaimed material, even with this material that's been sitting in ponds, sitting in storage, sitting in wherever, if it falls within a certain criteria, our models work really, really well. And this criteria is already being met by people commercially making this material commercially available now. So I'll tell you what, I think the future is bright. I think there's many tools. I'd like to do my best to answer if there's any questions. And again, check out the website, tylerley.com/fly ash, light it up, leave us comments, and check my YouTube videos out. Thanks, everybody. Enjoy your ACI. Take care.